Thank you very much for the introduction, and also, of course, I would like to thank the organizers for the invitation. So this is my third conference in a row. I must admit I'm getting a bit tired, but this one was the best. So it was really, really lovely, an absolutely amazing event. So after every single talk, I really had the feeling like I would like to work on this right now. So it's really amazing how the field advances, and it's really nicely reflected here in this conference. I'm really enjoying myself, so thank you very much for having me. We even had a birthday party, or a little type of birthday party, I guess. Okay, so Andrew couldn't make it, so I feel inclined to talk about this joint work with Andrew's, or honestly, as you can read. Actually, Andrew has done most of the work, so the whole idea is, I'm going to try to make this a bit clear during the talk, that whatever kind of algebra I'm going to study, those funny KLR algebras, we've seen them already, but they're really, really complicated algebras. And they're not as innocent as the Brouwer algebra. So the Brouwer algebra from the last talk is actually a beast. That was kind of the whole point of the last talk, but it's kind of easy to define. The KLR algebra is also a beast. It's really horrible in some sense, or very exciting. Depends a bit what you like to say, or depends a bit on your viewpoint. And eventually, I hope that this KLR algebra and its even more complicated cousin that I'm going to discuss today, eventually kind of the only really way to attack it is to probably have some computer to do it, and Andrew is doing a really great job to getting everything I'm going to talk about today into some Sage code, which will be available online, and you can run it yourself online in the Sage online calculator, and it will produce diagrams and compute the decomposition matrices and all that fun stuff. So Andrew is really amazing when it comes to those. So really high credits here to Andrew. Couldn't make it, sadly. Okay, I feel like I should at least motivate a little bit what KLR algebras are, or why are they interesting, and maybe I will give you a new perspective which you haven't seen before, why they're interesting. So here are also my role credits. I have the symmetric group and I have a related algebra, the KLR algebra. And yeah, so there are many reasons to study them. So I come from this categorification perspective, or to be completely precise, I come from here actually. So I'm a topologist. Nice to meet you. How are you? And here comes a reason to study the KLR algebra, which is kind of really, really amazing, and it's a not representation theoretical reason. So if you think about a problem, like here's a circle or a knot, and here's another knot. This was a really bad one. Let me try again. This is also, anyway, so there's some other diagram of a knot, and you might wonder whether they are the same or not. That's called the unknotting problem. And the unknotting problem is one of the most difficult problems in knot theory, and it's really, really complicated. So if you have a really complicated knot, and you would like to tell whether it's the unknot. So what knot theorists usually do is they study many of invariants, just a huge bunch of invariants that you throw at it, and you hope that the invariant doesn't give you a trivial answer. And it turns out that you can cook up an invariant using KLR algebras, cyclotomic KLR algebras of type A, to be precise, that actually can solve this problem for you. So the KLR algebra, the cyclotomic one, as soon as you have level 2 at least, level 1 is a bit too weak, but as soon as you have level 2, it's strong enough to actually give you an algorithm to decide this problem. I find very amazing. This is how I entered the field like 1,012 years ago. So this KLR algebra is really, really powerful. And also, this actually also tells you somehow that the problem can't be, or the KLR algebra, it can't be really simple if it can solve such a non-trivial problem. There are many other reasons to study it, obviously, and as we have seen already, many people here have worked on them. And eventually I would like to, well, find some nice basis for them. So the cellular basis. And yeah, so another reason why this conference is so amazing is that my talk went through something like 12 million iterations during this week, because I kind of want to address everything I've seen, which I obviously can't. But let me at least address the last talk, which I wasn't able to put on slides in the 5-minute break. I apologize. So what I would like to do is, I would like to find kind of this idea of having the iterated inflations applied to the KLR algebra. And what is an iterated inflation? Well, I draw a picture for you, which also fits very nicely to Stuart's talk, with one catch. So I apologize, there will be diagrams. I eventually need to say that anyway. So there are 4 ways to read diagrams. We have seen 2 of them already, and I will show you a 3rd one. So this was the last talk, this was Stuart, and I'm going in this direction. I'm very sorry about that. So if you're giving a diagram talk tomorrow, there's one more direction to go in case you want to test it out. Okay, so what I want to do is I would like to draw a picture for the iterated inflations, and my picture looks as follows. Okay, so I have a shirt somewhere up here. I hopefully wearing some pants, and I have a belt in the middle. And what was really nicely explained in the previous talk, for example, if you do it for the Brouwer algebra, so this should be kind of a way to slice my diagrams if you want. So what is a shirt of a Brouwer diagram? A shirt of a Brouwer diagram is one of those guys. What is a pants of a Brouwer diagram? It's one of, well, let me put 2 strings here. It's one of those guys again, maybe something like this. And what is the belt of a Brouwer diagram? Well, a belt of a Brouwer diagram is a symmetric group, so it could have a crossing here. Yeah? So the belt of a Brouwer diagram, the belt of Brouwer is a symmetric group. And essentially what you get from these iterated inflations is that, well, the classification will then go through some ordering, some cell structure, and the classification of simples, and the simples associated to the belt. And that's the whole point of these iterated inflations. And I would like to play the same game of these iterated inflations for my little KLR algebra. And this is what I will do. Very briefly, I will have a shirt, I will have a belt, and I will have a pair of pants. And for KLR, motivated by Murphy, these will be permutation diagrams. So if you think of the Murphy basis, it's exactly what Murphy would put on top. And there will be permutation diagrams on the bottom, whatever, something like that. I should probably have the same number of strands. And I will put an idempotent in the middle, an idempotent diagram, which is very boring, it's just strands. And it will be decorated with some dots. So the sandwich, so permutations at the bottom, top, permutations at the bottom, and the sandwich part is for the KLR algebra will be polynomial rings in those dots or quotients of polynomial rings. For example, if R would be some ground ring, ground field, whatever, it will be something like tensor products of those guys, for example. And whenever you see kind of a formula involving powers of 2, it actually is hinting that you have iterated inflation where everything in the middle of the belt is, let's say something like here, the dual numbers. And that turns out to be the case for the KLR algebra, or for all of these algebras I'm going to show you. And yeah, the point is, this is really a nice basis, and I don't want to split the middle any further. So if you would like to work with Brouwer, this is a great basis. Everyone likes the diagram basis of Brouwer. It's not cellular, so you would need to split the belt a little bit further to make it cellular, but in some sense you don't need to, which is the whole point of this idea of iterated inflations, which go back to Koenig and Xi. But as they point out, kind of a fun fact here, because I really want to mention one of my heroes, Brouwer. So Brouwer, quite a while ago, maybe one of the main names here connecting everything in this conference, right? If you do something related to finite groups, there will be a Brouwer somewhere. If you do diagram algebras, there will be a Brouwer somewhere. If you do cellular algebras, there will be a Brouwer somewhere. Because Brouwer had a PhD student, so gave the problem, understand the Brouwer algebra, to a PhD student, which is kind of a little bit of a mean problem, which was called Brown. And Brown came up with this idea in the 50s of the last century. It was obviously a little bit like 40 years before their time, so it never really catched up, and it took quite a while to be formulated properly, and you can find this construction than, for example, in this paper by Koenig and Xi, which I think has the same name. And anyway, I would like to apply that, and I would like to mention Brouwer, of course. I would like to apply that to my setting of the KLR algebra. And actually I have a more complicated algebra, so we'll have some very delicate combinatorics eventually going on. So I hope you will like it. I'm a big fan. So Ben Webster has this absolutely amazing idea, which I think is pretty good, to have some algebra, which I will call a wKLRW algebra. So KLR is KLR. W here is Webster, and I will explain the W, the small w, later. And this algebra is just a huge beast. It's just a tremendous family of algebras, and depends on many continuous parameters, which can all vary in the real numbers. And for certain choices of parameters, it will spit out, it will specialize to some of the algebras people really like, and people have really studied a lot, including semi-simple algebras. And the main idea, so if you want to have a look at the picture on the right, is somehow that if you vary those parameters, so you get eventually a picture like this, so up to some hyperplanes where something essentially different happens, as you can see here, sometimes in the right-hand side, sometimes you really change the nature of the curve, and this is just something where you can vary parameters. And so in each alcove here, it has a Morita equivalence class of those algebras. So they're all Morita equivalent, they're not isomorphic in general, but as you vary the parameters, you get all these Morita equivalent algebras, and then there's some singularity, and you get a new non-Morita equivalent, so those are non-Morita equivalent family of algebras. And we started this project by trying to understand Webster's construction, essentially, which was beautifully explained in a paper by Chris Bowman. And we are trying to the overall idea is if you understand this algebra, and then you can just vary your parameters, and you understand all of the other algebras as well. Which is a really, really fantastic idea, which I would like to sell you today. The diagram combinatorics is a bit tricky, but we will give it a go after I give you some simpler combinatorics. So, or actually the same type of combinatorics if you want. So my title promises crystals, so that's my starting point, but always keep in mind what I would like to do is I would like to write down a basis of a very complicated algebra, which hopefully isn't all that bad. It's kind of a very simple idea to have this shirt, belt, and pens picture, and it's a cellular basis, and classify symbols and all of that fun stuff that we all know and like very well. Okay, that's kind of the story. Just want to sell the picture on the right-hand side. Keep that in mind if you get a little bit lost in the combinatorics. The combinatorics is not so bad, but of course combinatorics is combinatorics. So we'll see. But let me start with a slightly easier part of combinatorics. I would like to show you some crystals and a proof. Every good talk has a proof. Oh, by the way, Chris told us that a good talk implies proof. So I'm kind of need to show you a proof, essentially, but there's also the converse, which is probably not true. So I'm going to show you a proof, and I leave it to you to decide actually whether I've showed the converse or not. Anyway, that was just a digression here. So a crystal, I don't want to define a crystal. A crystal is one of these definitions. If you see it for the first time, it's kind of non-saying. If you see it for the 7th time, it's still non-saying, but it's of course very important to make it precise. But people have done that. So a crystal for me in this talk is just a certain type of graph. And as we will see in about 10 minutes, it's a very, very special type of graph. It's not just a random graph. And a graph is something that underlies kind of a representation of some Lie algebra. So here we have a 4, that's SL5, and I should write the quantum group here, but I won't. So it's SL5, and the vector representation of SL5 should have 5, it should be of dimension 5, because it's of course just this guy here. And the action of, well, the Lie algebra or the Lie group. Let me write the Lie algebra and have the Chevrolet generators of the Chevrolet generators on C5 in the leading coefficient are determined by this graph. So the lambda one is the highest weight. It tells you this has the highest weight. If you apply F1, you jump to the next one. If you apply F2, you jump to the next one. If you apply F3, you jump to the next one. If you apply F4, you jump to the next one. And that's a very simple crystal, the crystal underlying the 5-dimensional representation of SL5. Hope that makes some sense. I'll show you some more examples, and then we do some very sophisticated crystals. Okay, so this is called an SL2 string. So here I have the SL2. I only have one generator in SL2. This one is bad. SL2, I can take, for example, the forced symmetric power, always confusing the off by one error. The forced symmetric power has dimension 5, and there are the 5 vertices. And the SL2 string is just exactly what you think it is. Usually, more often you will see this. Again, you need to turn your head. So most of the time you will draw an SL2 representation like this, and just the crystal likes it from bottom to top. This just really is the SL2 representation. And as you can see, there are various flavors. If you at one point miss a tableau somewhere, there's a tableau flavor of everything. I'm just labeling, usually just take the vanilla flavor on the left and label everything by kind of the weight spaces. And there's a PBW realization on the right as well. Let me show you some more examples, and then we do some more sophisticated examples. So here you go. This is SL5 again, and the 3 different realizations of it's still C to the 5 at the 5-dimensional representation. As tableau combinatorics, it's exactly if you apply 1, you switch the 1 to the 2. If you apply 2, you switch the 2 to the 3, and so on. And as a PBW, we just stack up the roots in this case. Good. Yeah, a few more examples. They get kind of funny. So in type D, you have the first appearance of what I call a face. So the 3, 4, so this little face here. How is it labeled? It's 3, 4, 4, 3. It's kind of a relation in the crystal. Little face on the right-hand side. So if I miscounted, it should be SO8. The vector representation of SO8 should have 8 vertices, and this is how the generators jump you through this crystal. Let's see, 4 is SP8, and B4 is SO9 or something. What do I claim? It's SO9, so you should see 9 vertices. Yeah, very nice combinatorics. Good. And the point is, and it's kind of well-known, that's where my thumbnail picture comes from, that this kind of reflects what goes on. So we will reflect that, the crystal will reflect the nice cellular structure on the KLR algebra, or on this funny version of the KLR algebra, it's not on the board anymore, the wKLRW. Maybe I should keep that. In the following way, so paths in the crystal essentially correspond to the belt. I'm going to explain that. And permutations in the crystal essentially correspond to the permutations. Let me explain to you what the permutations are. Probably I have an intermediate slide. Let me show you another face. Here's another crystal, and you can already see the face that I will call an octagon in a second. Let me try to get that octagon, something like this. Where's blue? Here's blue. That's a relation in the crystal and an octagon type face. Turns out that octagons play a huge role. Come back to octagons in a second. So we have seen squares and octagons. The PBW theorem itself is a crystal, which eventually shows everything you need to know about the cellular. This kind of part of the proof would be to realize that the PBW theorem itself is a crystal. So here's the PBW basis listed for, you have two generators, blue and red. So this is for SN3. And this whole idea is somehow very well known, but we will apply it here to this slightly weird situation that we'll see, is that if you take the Protch category projective modules of whatever type of correct KLR algebras, correct notion of KLR algebras, then this forms a crystal with the E and F generators that we have seen in Louis' talk, the restriction and induction functors playing the role of the Cauchy-Weyl operators on the crystal. And this is kind of the starting point, and this is why everything eventually will work. But I promised you a proof. Here's one of my favorite proofs. I would like to talk about faces, so I should make sure what a face is. So here comes a funny question. So can you actually embed a random graph, anything you want? Can you embed it in the plane? No, you can't. But maybe you can embed it on a high enough genus surface. So some graph, no idea. This one here maybe. Add a few more edges, I don't know, something like that. Can we embed that in some genus surface? Doesn't seem to be completely trivial, but here's a really beautiful proof how you can show that there's some genus, so you can embed this beast on a high enough. We'll tell you in a second. So here we have a little handle, and a little handle, and a little handle. So here would G, this is a G, G would be 3. And how do you do that? Well, just imagine you're a city planner, and if you're a city planner, it's very easy to get rid of crossings. So this is not embedded because of crossings. But if you're a city planner, you know how to do that. You just build a bridge, right? A bridge gets rid of crossings. So I just build a little bridge here for all of my crossings. And a bridge is, of course, nothing else than a handle. So I can embed this graph into this surface here. I could do better. I'm not saying this gives me the optimal G, but this gives me some G. This is a very cute proof, actually. So you just build, every city planner would do that, right? You would just build little bridges. I would like to use this to think of a crystal as living on the surface or on some surface. And then I can talk about faces, because a crystal then will give me a polygon decomposition of whatever, this genus G, genus 3 surface. And you might ask, well, kind of obviously if I start with a random graph, I can get any kind of polygon decomposition I can imagine, you can imagine here. But maybe, actually crystals are very special, and you don't get too many funny faces here. We've already seen this one, and we have seen this one, and there are not many more. It's kind of a fun fact about crystals. This is a square, this is an octagon, and it turns out that it doesn't get much more complicated. Oh, go ahead. It turns out there's a fun result by a ridiculous fact that was for any finite dimensional representation of Lie algebras of finite type is the worst case scenario is this. I needed to look that up. It's a 14gon. So a tetradecagon is a kind of the worst case scenario that you will see in a crystal. So the worst case relation you can see in a crystal, like I think of this as being a relation with two colors. Right? This is an SL3 string, and the worst case we have is a tetradecagon. Let me pull up a crystal for you to convince you that this is a highly non-trivial statement. So can I move this? So here's F4. So this is a crystalline type F4. And you can already see here is a square, here's another square, a lot of squares. And towards the middle you see the famous octagons. And then the squares again, squares again, squares again, a lot of squares. But those crystals get really, really large. So let me zoom out a little bit. So where are we? Maybe we go to 70%. Here again, the next crystal, so this is the number 4 crystal. Again, kind of the same pattern. You see plenty of the squares. You see the octagons. Let me pull up another one for you. If you do something like, it's highly non-trivial. And it's really surprising that this is true. So I hope you like that statement. It turns out, well, I'm going to tell you in a second why I want that. the feed page. So this is really complicated already. And if you look carefully, you will find, let's see, green, red, red, green, red, green, green, red. There's an octagon. There are plenty of squares, and if you stare on this carefully, you will not find anything else than an octagon or a square. So the first crystal in finite type, where we'll see some of the others, which I can't show you, it was too big for me to compile it and put it on a PDF, is if you take the F4 graph, and it's the lambda 2. So if you take the lambda 2 crystal, you will see all of them appearing, and that's the smallest example I know. And that crystal has around 1,000 vertices, so I wasn't able to put it on a PDF for you. But it's really remarkable. If you just look at this beast, so imagine it's embedded somewhere, and you will only find those little polygons. Very remarkable fact about crystals. And why does it play a role? Well, it turns out that there's something you need to prove. I only mentioned this for the following reason. There's something you need to prove, and you need to prove that in quite some generality, but it turns out there's only a finite number of cases you need to check. So all of these correspond to relations in the KLR algebra. So on the flight here, I did the decagon. I'm very positive, well, probably not, we'll see, but we'll see about the final one. So it's a really beautiful diagrammatic description or a diagrammatic equation for the decagon, for example, between a 5-strand diagram and another 5-strand diagram. It's really, really tricky, and it gets pretty crazy. I would have never guessed that this is true, but it turns out to be exactly what you need. And Stembridge and Sternberg told you how it works, kind of quite a while ago. So history here is Stembridge did the simply laced types, and Sternberg did the rest. And in case you're wondering about type A KLR algebras, so type A crystals that appear for KLR algebras will only be of those type, and the relation here is the Reidemeister relation. So this one is easy. For the other ones, you need to worry about those bigger type of faces. And there's only finally many things you need to check. Okay, so I would like to use the remaining time to explain this algebra. Right now we haven't touched it, obviously, and I'm very lucky that a lot of people have done absolutely fantastic work on diagrammatics. In some sense, my diagrammatics is in some sense much easier than the diagrammatics of the Brouwer algebra, because I essentially only have string diagrams. If you want to invent a symmetric group, I kind of immediately start drawing those diagrams. So this I'm using one-line notation in contrast to the previous talk. So here, the permutation, maybe I can do this here. 1 goes to 2, 2 goes to 4, and so on. Whatever. 7 goes to 6, 7 goes to 6. Here's another one of them. And that's a symmetric group. That's a string diagram algebra. Of course, we all know by now how this works. I remind you that I'm reading in this direction. I'm very sorry for not keeping the same conventions, but of course you just stack them and get a new string diagram, which you simplify. And as we have seen in the last talk, it's not really a diagram algebra. It doesn't really matter how I draw the diagram. So it's more like a nice pictorial way to think about those pictures. And the point is, we have those relations that we all know very well, which are called the Reidemeister type relations. If you think of something that is a string algebra, these are the only relations you could think of anyway. So the Reidemeister 2 relation and the Reidemeister 3 relation. Good. And in the symmetric group, everything is beautiful, and you can just pull strings from left to right and do whatever you would like to do, and just beef up that calculus, and whatever comes out is this algebra here. Let me just mention that in case exactly what the last talk said. Actually, these are not really diagram algebras, what I showed you so far. They're not really using anything, any geometry of the plane or anything like that. It's just a convenient way to think of those diagrams. But this idea of Webster is to really use the geometry of the plane. So I will show you a diagram algebra where all the inputs, like where the strings are and so on, which matters for this weighted KLRW algebra. So the W, the small one, is weighted, and I will explain in a second where the name comes from. But what you should keep in mind is that I will show you a diagram algebra, which kind of lives somewhere in R2. This is my really bad picture of R2, so R2 is the box. And the positions of the strings matter. There will be some strings, and they will cross, and whatever. And the positions will matter. So I can't easily move the string around. And these are exactly the parameters in my algebra. So moving those parameters around, the strings around, will change the nature of the algebra itself in this nice little hyperplane picture. Keep that in mind if you get a little bit lost in the combinatorics, which will happen now. Awesome. So I beef up the diagram calculus as follows. I will have 3 types of strings. I will draw them in a second, and you can ignore one of them, which is a didactically really a horrible thing to do. I just show you 3 types of strings, and I will ignore one of them. But I will. So I will just say a little bit about it. So I have 3 types of strands and I have 3 colors. That's awesome. Okay. So I have a red strand. I have red strings, and they are labeled by fundamental weights of whatever type of Dynkin type I have. So I can just give them I, the label of the vertex I. So maybe we have some Dynkin type here, whatever, something simple, and I will label things by I, and I do the same for the solid strings. So here's a solid string, very good, labeled by some other number J, and then there's a ghost string, which is kind of the whole point, and is also labeled by J, and we'll see that in a second what happens. But we have 3 types of strings, and the number of, I will ignore that in a second, but the number of red strings is a level, in case you wonder. Okay, so I told you that level 2 is needed for the statement about the knots, like the unknotting problem. And yeah, I will only stay in level 1, so you will only see ever 1 red string. Just right now as a disclaimer, nothing I really do depends on level 1. It's just, I'm just super lazy. And I only like to draw 1 red string. And kind of what I like to think about, because everything here is flexible, is some red string, and it kind of is positioned at 0. So it kind of anchors my diagram somewhere. And the only really attention you need to pay is what the other strings are doing. All right. I will answer that in a second. Oh, the label is on the top. No, here comes if you have never published a paper with a lot of diagrams and a lot of colors, eventually someone will complain that it should be readable in black and white. So you come up with some ideas how to make it readable in black and white. So you just put the label on top. And if you just text that for like half a year, then you get so used to it that you just put the label on top. I'm very sorry. Okay. Oh, I should mention the dots. So there are also decorations which are dots. These are the polynomial parts. So the y is in Luis's talk. The dots that move. Right. And the input is always a quiver, something like that. And it's really the quiver, so the orientation will matter in a second. So it's not quite the Dynkin diagram, it's a quiver. So some orientation on those beasts. And the whole point is, well, if you think about it a little bit, it's a string algebra, so there can only be those relations. It's impossible that there's anything else, essentially. And the whole point about the KLR, or the same for this algebra, is that they hold spot on or not, depending on the labels. So sometimes you have a deformed relation like this one, right? We had that in Robstorp, for example, as well. So it's deformed because you just can't pull it straight. You just get these error terms with the dots. But that's the whole point. So I won't write down the whole list of relations. It's not so bad. It's just those in some deformation. Very good. Here comes the point. Let me try this. So what you do is you have some red string that sits somewhere and anchors the diagram. Let's say it sits at 0. So in this diagram now, what you see at the bottom are the positions along the real line. So I have a red string sitting at 0. I have, what do I have here? You can really choose anything, 0.5. I'm not very sophisticated. I have a pi here. I have a pi. Very good. I have pi and whatever you see upstairs, minus square root of 2. I hope the spacing makes some sense. I haven't thought about it too much. But you have this whole data. So you fix this whole data where the strings are. Okay? And then you associate, and now comes the tricky part, you associate to, let me do this very, very slowly. You associate to each arrow in the quiver, let's say it goes from I to j. So if you have now a blue I string sitting here, then it gets a ghost, which I will draw again like this, sitting a certain amount to the right. And the amount to the right is encoded in another parameter, which is the weighting of the graph. So graph theory, weighting of the graph, you put another real number here, and this real number is the distance between, maybe I should call it x. And this number is the distance between those. If it's negative, you put it outside. And the point is, it kind of gives this string a thickness. So this is kind of its right part and this is its left part, because the relation in the algebra will be that the ghost is always mimicking its parent string. It goes around and around. I hope this is a good picture. It's always mimicking its parent string, which I'll show you an example in a second, which prevents me from moving strings arbitrarily around. Because it essentially have a thickness. So here maybe somewhere here is the ghost of this one. And if I move them around, I will move out of certain strings, and some strings move in, and so on. It kind of prevents me from doing that freely. Sorry? Yes, as you know, it's very parallel. It's a J string. Oh, very good point. It won't play a role anymore, so I forgot it. Depending on the orientation, if the number is negative, what I will do is, so if the number is positive, the source gets a ghost. If the number is negative, the target gets a ghost. And as you can see, the J string, it has a parallel ghost, 1 unit to the right. Yes. So it has kind of a little bit of a bias. You push everything to the right. You need that for some silly reason, making the algebra itself independent of the choice of the orientation change. So if the ghost shift is very small, it will mimic it the very, very small amount to the right. So the weighting is really the ghost shift in this picture. Okay, here's another example. Coming back to your question, so if you have something like this, what is in my quiver, this really works for any graph. You can do this for any graph, not just for the finite types. So you can have something like this. And depending on the labels, so epsilon is a very small positive number, 1 minus 1 epsilon. If this is the I string, then the I string actually gets 2 ghosts. This one and this one gets a ghost as well, which I hopefully did correct. So the K string gets a ghost because it's a minus 1, shifted 1 unit. The I string gets 2 ghosts, one of them shifted a tiny amount, and the other one shifted 1 unit. And they always mimic their parents. So in the second picture, same, you have 2 ghost strings, shifted 0.5 units and shifted 1.25 units. Hope that makes some sense. That's right. But the point is, there's an extra choice involved, which I don't like, the orientation. And in order to get rid of the orientation, I could redefine everything. But the point is now, because if I reverse the orientation and swap the sign, then the algebra is the same. I get rid of this choice of having an orientation to begin with. It's just necessary to draw the correct diagrams. And here's the point why they get stuck. So let me just redraw the diagram for you. So I could have an ij here. This is an I, I'm very sorry. And what is it, a k? A k is somewhere sitting very far away. So let's say this distance here is, can I come up with a large number? 101. That's a very large number. The largest number I can come up with. And here's an I ghost. Here's a j ghost. And locally, it's kind of the fun. Why is this a really diagram algebra? Why the planar geometry matters. Locally, it looks like I can pull them close to one another. But I can't. Because at their right ends, they're actually stuck. There's something string in between. So either they look locally close, but they are not. Yeah, and this kind of gives the whole thing its flavor. So I can't arbitrarily move my J string here closer, and my I string. If I would move a little bit too far, then actually I get stuck here, and I can't do anything anymore. And this gives it its flavor. So you can't move strings arbitrarily. Everything depends on the previous choices. Let me explain the hyperplane picture, and then I just state the main result, and I'm done. So I'm not going over time. At one point, you need to sacrifice something, and I will sacrifice the main result for the hyperplane picture, which is due to Ben. So Ben has this worked out, Ben Webster, very nicely in the first paper on this. So it's the following idea. Maybe I just do it here or live. So if this is the position of the blue string, so blue, and this is the position, very good, of the red string, red. Then I have 3 hyperplanes, and the hyperplanes are exactly when the strings match. So if I take the first picture, which looks a little bit like this, has a ghost string somewhere here, and the red string is sitting here, and I move this string a little bit rightwards, eventually it will hit the red string. This is where the hyperplane is. That's where the algebra is not defined. And I jump over, and I get a new equivalence class of algebras. So 2 non-trivial facts. So first, in each alcove, so you just draw the alcoves, yeah, in a very high-dimensional picture where strings would collide when you just move them around. The alcoves are Morita equivalence classes of the algebras, and in various alcoves, you have the various strings sitting. So that's kind of the picture. So if you vary it a little bit, you go from those various algebras. You can make it very semi-simple. How does it get semi-simple? I won't explain how the others arise, but how does it get semi-simple? Well, if, for example, every strand here is just very, 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 very far away from its ghost, so they don't really interact. Everything is just very spread out. That's the case where the algebra is semi-simple. Because you have those types of relations here, and you can just pull strings freely. So the interaction relations, the Reidemeister relations, happen between all of these possible strings, and if they're very, very far apart, it doesn't matter, and you just you don't care anymore. You can just move everything around freely. Hope that picture makes some sense. So that's kind of the idea of Webster. We have this huge algebra, which is not so bad. I mean, it takes a while to get used to the combinatorics. There's a lot of data, but that's the whole point. Because now we can vary all parameters continuously. We can vary those parameters continuously. They are all in real numbers. We can vary the original positions of those strands, whatever, my pi or minus square root of 2. And this huge variation gives you access to a lot of algebras, which is kind of really cool. I really like this a lot because this is very different from all classical diagram algebras. Some games you can't play with classical diagram algebras. And let me just mention that I don't go into details. I only have something like 5 minutes left. As soon as you see hyperplanes, there should be a theory of translation functors which jump you around, and indeed there is. There will be functors relating the various Morita equivalence classes of the algebras. You can kind of imagine how the functors look like. They will be generated by those pictures, if you want, right? So the crossing type picture. And you get this whole theory of how the various algebras are actually related that look very different from the outset. It's a really beautiful picture. that Ben came up with about 10 years ago. Okay, I'm running, well, it's okay. I have 4 minutes to go. So I just show you now the main theorem. The main theorem, I can nobody tell you, it's sandwich cellular with those guys being permutations given by the Sternberg-Sternberg, so just walking around the crystal, the Sternberg-Sternberg permutations. And this one is an idempotent you get from the diagrams, and I will explain to you how that works. That's exactly what it is. So here's my shirt, belt, and pants picture. I don't read the text, it's not so important. But that's the whole point. And let me explain to you how to do that. The last missing ingredient is my idempotent in the middle, and it corresponds to, I will do an easier example for you, and you can double check with the above example. It corresponds to a pass in the crystal. So what I could have, for example, is my crystal from before, 1, 2, 3, so this was 4, 5. This was type A4, so SL5. And what you do is the following. So you have this defined. So kind of the point is you need to figure out what idempotents to put to give you a basis, and the crystal will do the job for you because essentially it draws for you a PBW basis. And it works as follows. It's pretty simple. And the computer can do that, and you can do that. And even I can do that. That's pretty impressive. So you have a red string somewhere, and it's just, this was lambda 1. It's just labeled by, remember this is 0, right? Here's 0. It was just labeled by the highest weight. And then, well, what you're supposed to do is you put a 1 string, a 2 string, a 3 string, a 4 string, a 5 string, and you always place them in the shadow of the previous string. So let me just say my shifts are all 1. So I place the 1 string, it gets a ghost somewhere here. I place a 2 string in the shadow of the other one, it gets a ghost somewhere here. I place a 3 string in the shadow of the other one, it gets a ghost somewhere here. I place a 4 string, it gets a ghost somewhere here, and so on. Oh, this is 3. It defines you. Very simple, actually very, very simple. Just place it in the shadow of the previous string. And if I haven't messed up, then this is what's happening on the slide for this crystal. You see octagons again, you see squares again for this crystal in type B3, I guess, I think. And that's it. That defines you everything, essentially. And the main theorem is, oops, this was too fast. The main theorem, so I need to point out some names here in case you don't want to read. This is my picture of affine type D, in case you don't remember what affine type D is. It's the one with a double fishtail. So it turns out that this procedure works. I will have a better slide in a second in quite a few cases. So it always defines you a basis. And the question is whether the basis is a cellular basis or not, or an iterated inflation in the sense from before. So the shirt, belt, and pants picture. And it turns out that based on work of many people here, which I'm very grateful for, I will comment on this one in a second here because it's kind of an open question. But let me just show you. So the whole point is, we are not there yet, but I hope there is just some criterion that you can read off from the crystal that tells you whether the algebra is cellular. And it works in the cases I've checked. So by cellular, I mean in general for any possible placement. Obviously, if you have 0 strings, the algebra is trivial, so it will be cellular, but I mean kind of in general. It turns out that the KL algebra and this algebra and their cyclotomic quotients are cellular in the marked types. They're not cellular in the crossed types, and I can't tell you right now for the other types. And essentially, how to do this is to read it off from the crystal, but I'm out of time, so I can't explain that anymore.